Hello, this is my presentation on linear regression. Origin of linear regression traces back to the late 18th and early 19th century. The method of least squares was founded by Carl Friedrich Gauss and Adrien-Marie Legendre. 1805, Adrian published the new methods of his work in The New Methods for Determining the Orbits of Comets. There he introduced the least squares criterion. In 1809, Carl Friedrich Gauss claimed he had been using the method since 1795. He formally described it in his book of Theory of Motion of Heavenly Bodies. The method was initially developed to solve problems in astronomy and geodesy, such as predicting planetary orbits and determining the Earth's shapes. These fields required methods to fit models to noisy observational data. Regression analysis was the solution. Gauss's work on the Gaussian distribution, or the normal distribution, further cemented the link between linear regression and probability. The term regression was introduced by Francis Galton in the 19th century in the context of hereditary studies. He observed children's heights tending towards the average in the population rather than the parent's height. Galton's work inspired Carl Pearson, who formalized the theory of regression and the correlation coefficient, laying the groundwork for modern analysis. By the early 20th century, linear regression was widely applied and studied in economics, biology, and social sciences. The developments in matrix algebra and statistical theory during this time allowed for the generalization of regression to multiple variables and more advanced methods. Linear regression remains one of the most foundational tools in statistics, data science, and machine learning due to its simplicity and interpretability. So the least squares method is a statistical method used to find the best fitting line or model by minimizing the sum of the squared differences between the observed values and the predicted values. We want to find a linear model that is close as possible to the observed data. The objective is to minimize the sum of the squared errors, which is essentially comparing different models and choosing the one with the lowest summation of the dashed purple or green lines shown in the figure. Here is that concept as a formula, the SSE, sum of squared errors, where yi is the actual observed values for the ith data point, and yi hat is the predicted values for the ith data point. So, how do we find the parameters b1 and b0 such that the SSE is minimized? We use calculus by taking the partial derivatives with respect to b0, b1, set them to 0 to find the minimum. The result of solving the equation is here, where x bar and y bar is the mean of their respective values. Here's an example of the least squares method being used. We have our data, x and y. We've calculated the square of both and the product. To calculate x and y, I'm going to use the observations, number of observations, which is 8, and the summation of each column, which is the bottom row. Calculate our model using the formula. Now we can put our model onto the graph. This is the line of best fit. Moving on, we can create a new chart called the residual plot. The residual plot shows us the pattern of change along the trend line, useful in many applications such as economics. Residual plots are used to check the model's fit, identify patterns, and overall evaluate the model's usefulness. So there are some key assumptions for these models. The first one being linearity. The relationship between x and y must be linear, which means the predicted y is a linear function of x. It's easy to identify linearity by looking at the relationship between x and y on scatter plots. Clearly, these plots are non-linear, whereas this one is more linear. The relationship would be more suitable for a regression model in the second instance. However, given that said, independence of errors is another key assumption which should be considered. There's our model, looks to be linear, but upon evaluating the residual plot, there's a clear pattern there. This suggests that there is a positive autocorrelation. We don't want this. We want it more like this, even scatter above and below the line, negative autocorrelation. Next pattern to look for is homoscedasticity, constant variance of errors. We don't want that sort of shape. That means high values of x are going to be unreliable in the model. We want it to be more like this, parallel, even scatter, no deviations in variance. Normality of errors, a key assumption for many models. We want the errors to follow a normal distribution. Extreme values less often, average values most often. We can assess this using a QQ quantile plot. It works by ordering the percentiles in the standard normal distribution and then comparing it against the residual line. The straighter the line, the more likely it's going to be normal, making hypothesis tests and confidence intervals more reliable. Multicollinearity. This is for multiple regression. We don't want highly correlated variables together, such as number of rooms and house prices. These relationships can make it harder to isolate the effect of each variable in the model. We can use correlation matrices. In this example, this is going to be a highly correlated variable, which should be omitted. We can also use VIF to help us quantify and address these issues. Finally, let's discuss sample size and data quality, which are critical for reliable regression analysis. Firstly, the sample size should be large, at least 10 observations per predicted variable. Next, data quality. The data should be representative of the population, also have no errors or outliers. Outliers here, as shown, can disproportionately influence the regression line. This single point has skewed the regression line to far less steep than it should be. These can happen through variability in data, human error, or measurement issues. To detect outliers, we can use different methods, such as the box plot method, where we take the interquartile range and any observation 1.5 times beyond the interquartile range are flagged as potential outliers. By addressing outliers, we can ensure adequate sample sizes and we improve reliability and interpretability of our regression models. That's been my presentation on linear regression. Thank you for listening.